Greetings everyone and welcome back to the bench. I've been itching to get back on this amplifier project, the Discrete audio amplifier design and build project as I call it. Like I said, I've been dealing with work and other things in my life which has been keeping me from making a lot of videos lately. But anyhow, to bring you back up to speed, in the last project video I was dealing with the oscillation, and I believe I have it solved. And I found out that I needed better bypassing of the supply rails near the output stage. So let me give you an example here. This is an LM1875 board. Those really nice boards, really nice laid out. I used my own parts. I wanted to get high quality parts, and I'm going to build these into an amplifier at some point. And they're really nice boards. I need to clean the flux a little bit there, but very nice ground layout. And see these ceramic caps? Well, these are supply bypass. These are electrolytics, larger supply bypass, but these ceramics are really close to the supply rails of the chip. Of course, the output stage is going to be inside the chip. But here's my folly. These blue ceramic capacitors, I put them over here, and they're pretty good distance from the output stage that handles a lot of current. Well, if you watch my videos, it's not like I don't know this stuff. I preached it in earlier videos I made years ago, but I didn't heed my own practice here and ended up getting a bite in the rear. So yeah, you got to do this stuff. I mean, I did lay the board out nicely. I thought everything star grounds in, the grounds each star ground into the capacitor, bypass capacitor section. Here's the ground area. All the grounds come in at their own point here. The small signal ground, the large signal ground. Same with the supply rails. The the output stage has its own line going to it, and the smaller signal parts of the amp have its own supply rail, its own line coming into the filter cap area of the board. Heavy signals from the output stage are not traveling on the same line that the smaller signals are, which could cause instabilities and oscillation. However, like I said, it's just too much. With these high-speed transistors, transition frequency of 30 megahertz, I believe they are, they're just so fast that it caused problems. This line here, I used heavier copper, kind of doubled it up. It's about 6 centimeters, which is not a lot. If you look at a lot of old amp boards, that can be much bigger than this little board here, but it's enough with these transistors for them to oscillate. So what I've done here is I've taken this vinyl coated wire, these black wires, they're connected to the ground. I brought them out here and brought them near the supply rail so I can run or place a ceramic capacitor across the supply rails near to the output stage. And that did it. It took care of the problem. Now granted, there still could be inductance in these ground leads here. There still could be inductance, and you could still have a problem. However, when I lay out the boards to have them professionally made, I'm absolutely going to do much better grounding and much better with the supply rails. I'm going to have ceramic bypass caps near to the output stage. So it'll be better than what's going on here. However, this happens to be good enough that it is stable. So that is very good. So what was actually oscillating? Was it the drivers or the outputs? Well, I'm pretty sure it was the output transistors. because when I had the 100 picofarad Miller caps around the drivers, that's plenty to kill a 40 megahertz oscillation. That's a really high frequency, and those 100 picofarad caps should have taken care of that if it were the drivers. But if you remember, when I added them in, it really didn't do a thing. So it couldn't have been the drivers oscillating. It had to have been the output transistors. When I added the bass stoppers, it really did reduce that by almost an order of magnitude. But it didn't kill it. It was still, the bad supply bypass near the output stage. So yeah, I took out those Miller caps, and I'm going to leave the stopper resistors in there. I think they're good to have in there. I might experiment by shorting them out with a piece of wire, just to take them out of the circuit and see if it oscillates now that I have the bypass caps near to the output stage, like I mentioned before. So yeah, I think we're getting somewhere now. Okay, so what I'm going to do today in this video is I'm going to apply some waveforms to the amp. We're going to look at sine wave and clipping, see what it looks like there. Maybe do another power measurement now that the oscillation is taken care of. And we'll look at the square wave performance of the amplifier. We'll see, we'll check for oscillation or ringing when we add capacitive loads. Some people in the last video are playing with generating fast square waves with what I had here on the bench. Some people were saying amplifiers don't really need to work that fast. Well, I'm not really testing amplifier speed. In a way I am. I kind of see how it performs. What I'm doing is mainly looking at the stability with capacitive loads. In the real world, the amplifier is going to have to deal with those, and if it's not stable under capacitive loads, that's something that's got to be fixed. So what way to better challenge the amplifier with fast rising edges and putting capacitance on its output, pure capacitance right across its output, to see what happens. So that's what I'm going to do here. Here's a simple schematic of the circuit. Input the 10 kilohertz square wave. 10 kilohertz it doesn't have to be exact. We're not really concerned with the frequency. We're really looking at the rising and flat edge where they intersect, and the falling in the flat edge where they intersect, and seeing what's going on there, if there's ringing and such. So like I say, we inject the signal to the amplifier under test, and it's important that we put a load on the amplifier. We want the amplifier handling current, and most tests they use an 8 ohm load, but I'm going to make it more challenging and make the amplifier handle more current by using a 4 ohm load. And I'll test it without a capacitor, and then I'll start adding capacitors. I'll try we'll start at like 1 nanofarad, and then 10, and 100, and then maybe 220, and up to 1 microfarad. Now 1 microfarad is probably more pure capacitance than you'd ever put across the output, so that's pretty brutal test, really. In fact, the square wave test is a pretty brutal test, especially if you're going to test at high signal levels with low impedance loads. You can cause a lot of dissipation in the amplifier, a lot of continuous current handling. So if you're repairing amplifiers for, amplifiers that are not your property, you're repairing them for a customer, I would recommend not doing this test, at least with high signal levels. You can do it at lower signal levels, but be careful that if the amplifier does break out into heavy oscillation, it could possibly burn certain parts of the amplifier, or blow the output stage. So it is a pretty brutal test. But again, I really want to flesh out any problems with this amplifier. And this is not the be-all end-all to stability tests. There's other tests I need to do, like phase stability, and that'll come in a later video. Alright, I have the little heat spreader mounted back onto the board. This thing's been on and off so many times. I reapplied the heatsink compound. Make sure there's no grit. These little TO220 transistors are going to take a beating. I probably should have found a way to use these on the board, but I've been through that so many times. Like I said, same exact transistor inside, it's just these are cheaper, great for tinkering. But of course, they won't be able to dissipate as much heat as these. You know, these are monsters in size compared to those. And re-grease up the back of the board and mount it to this massive heatsink. This thing is huge. Look at the back plane. See how thick that is? That's the way a heatsink should be made. Fin should be a bit taller though, but this should do the job for us. So I will get this mounted on here, clamped down, and we'll do some tests. Okay, I have my little thermal jig set up, as I call it. Have the amp mounted to the big heatsink here. Got it clamped down. My spreader should be a little bit longer here so I could clamp it better, but this is pretty tight. I removed that filter cap from the input for the square wave tests. Power supply hooked up. Got to get the scope hooked up. Non-inductive 4 ohm load. Now this is made up of two non-inductive 8 ohm resistors in parallel, and it'll handle 40 watts. However, with the square wave test, with the signal near the maximum point, you know, right near the supply rails, this thing's going to be dissipating a lot of power. It could go way over 150 watts. But, you know, that's okay because it's only going to be a short-term test. And like I say, with these small transistors, I cannot push them too hard for too long. And this is just a junction to the preamp. I'll have my signal source here. First we'll do the sine waves. I have to find my music player. It seems to be MIA. And we'll continue on. Okay, so I have the power supply on, and we'll get you pointed to the scope. Plus minus 32 volts. 3.2 amps. Let's see what we get here. Get a little signal flowing. Ah, nice sine wave. Do you see any oscillating? Ooh, I don't see a thing. That's a beautiful little sine wave we got there going. There is clipping. But I see a problem. Look at that. It goes up high and it jumps back. You see that? That's a problem here. I don't think that's the amplifier. I think that is the power supply. It might be, let me see here. Power supply is not hitting current limit yet, but I usually see that I need better supply bypass, larger filter caps. It might be a supply current limiting issue. But as of now, we're putting out 18.2 volts. So let me get a quick measurement. See how hot these transistors are. Well, bias stability is wonderful. You know, after that burst of heat, it's staying stable. That's very good. So anyway, where's my calculator here? 18.2 volts RMS squared divided by 4. About 83 watts. So yeah, the amplifier's doing fine. Like I say, my supply can only go up to plus or minus 32 volts. When I get the proper supply on here and get plus or minus 35 or maybe 36 volts, depending on how it sags under load, it might be able to hit 100 watts into 4 ohms with this thing. For now, let me see if I can take care of that little notch that's forming on the peak of the sine wave there. Okay, so here's what I've done. I've taken these old Nichicon 6800 microfarad caps. It's the only value add sitting around here to use. I soldered some clip leads onto them. Make a dual rail power supply filter here. So we have red for the positive rail, black is the common, and blue for the negative. I don't have the right color alligator clip cover, so that's why that looks like that. So I'll just clip these on to the power supply of the amp and clip the actual power supply here to the capacitors. So this will be nice to have around on the bench if I need to stiffen up power supply rails or something. And I hope that takes care of it. If I didn't mention before, I've seen that issue when using my old Radio Shack power supply testing chip amps. When it wasn't delivering enough current, you kind of get that weird, that shape on the clipping. Okay, so power this thing up, turn the amp on. Nothing goes bang. Okay, that's good. Getting the proper currents. Turn on the signal now. Here we go. Oh, look at that. Nice clipping. Now it's nice and flat. Symmetrical clipping. Did it give us any more output power? Stiffening up those rails. Oh, wow. Yes, it did. It did give us more output power. 19.1 volts this time. Let's see how hot our little transistors got. And they got a little toasty. So 19.1. Square that and divide it by 4 ohms. Just adding these stiffening caps, even though we are on a regulated supply and the supply is not complaining about overcurrent. So adding those to the rails, those caps, now the amplifier is putting out 91 watts into a 4 ohm load. So we went up from, what was it, 83 I think, to 91 watts with a plus and minus 32 volt supply. This little amp is impressing me more and more, but I'm hoping it survives the square wave test. Now with these caps now on the rails, we can make something go bang. They can deliver quite a bit of energy into the output transistors if something goes wrong, and things can go bang. I hope not. So now I'm going to move on to the square wave tests. Okay, it's square wave test time. I'm using the microcontroller that generates fast square waves. Potentiometer, I can adjust the level. Connected the amplifier up here. Now I did put earplugs in my ears because if something goes bang, it'll go bang pretty loud probably, because the those capacitors can deliver a lot of energy. So let's see what happens now. I'm going to crank this up a little bit. So it's nice looking square waves. It's 10 kilohertz. Let's take this all the way to the top. Oh, my power supply is going into current limit. I'll turn that down. Well, near saturation, the transistor should not get that hot, but around the midpoint, they'll get scorching hot. Yeah, my power supply goes into current limit because, the square waves are going to draw a lot more current than a sine wave, because, the square wave comes up to a high level quickly, goes down to the bottom rail at its highest level quickly. Of course, the square wave is going to draw a lot of energy having the flat tops and bottoms, And the maximum power my power supply can deliver is 200 about 205 watts really, and that's what the amplifier is drawing, since it's, you know, the power supply is set to its highest voltages and current. So the amp's drawing 205 watts, and much of that is going right into that resistor. Okay, I set up the oscilloscope. I moved the trigger point over here so we can see the whole waveform. I'm also triggering on rising and falling edges so we can see both at the same time. And according to Bob Cordell, he says set the signal to about 5 volts. So I'm about around that level. And I'll start with a 0.01 or a 103 type film cap, which is 10 nanofarads, 103, across the output, and that doesn't do anything, no response. So I'm going to move up to a 0.1 or 100 nanofarad, and you can see a slight ring, mainly on the top there. So it's fine, we're doing okay. So we'll move up to a 0.22 or 220 nanofarad. See what that looks like. Okay, so we're getting a ring, but it's dampening it out, so that's pretty good. Now we'll jump up to 1 microfarad. Some say this would be quite excessive, but why not? Just to see what it does. Okay, so we do get a ringing, but it's damped out. It doesn't, you can see it damps it out by the end of the waveform. So I would not really be concerned with that, as long as it damps out. If it broke into a continuous oscillation, you'd know we have a big problem there. Okay, so now I'm going to look at a larger signal. Let's turn this back up to 10 volts. You crank that up. Here's over limit. I gotta be really quick here because the amplifier dumps a lot of energy into that resistor. And let's put that on the output. I'm back to the 0.22. Okay, it actually looks better at higher signal levels. I'm going to turn that off. It gets really hot. And I'm going to dare try the 1 microfarad at that level. Let's see what happens. Huh. It's not bad at all. Let me turn this down a little bit. We're close to clipping. I gotta let the resistor cool off a bit and come back. I don't know if you can hear the booms in the background. I think the city's putting on a fireworks show. It's July the 3rd at night. I figured they'd do that on the 4th, but oh well. Okay, let's try this again. Man, putting that 1 microfarad cap across the output makes sparks fly from the leads. Yeah, it's a little ringing, but nothing serious. I am quite impressed. Well, I think I'll wrap this up here. A little thermal jig did its job. This got warm, but not really hot. It did keep those little transistors cool enough that they survived the tests. Now this test might be considered out of order. I probably should do the phase stability test and then run this test. I might have to tweak the compensation capacitor, which might affect the stability doing these capacitive load tests. But that's okay, I can run through all those tests again. Might even look at tweaking this coil. This is in series with the output. There's a coil wrapped around a 10 ohm resistor. So that coil is in parallel with that resistor. It's called a teal network. And that helps the amplifier dealing with capacitive loads on its output. And when I bypassed it, I did it off camera with the 1 microfarad. The oscillation was still dampened, so the amplifier is still doing pretty good even without the coil there. But it's really a good idea to have it, because you'd have to do a real thorough test of all different capacitor values, and maybe you might home in on a resonance with the capacitance and a parasitic within the amplifier that might cause an oscillation. So it's a good idea to have the output coil. But that'll do it for this one. Thanks for watching. I've never seen a cat go so crazy for water. It's just water. It's not like it's food. You get water all the time. He wants his water! Water! Alright, you can't keep the water from the kitty. Watch out! God, let me put it in there. There you go.